Hi, Gabriella. So what I did is I changed your data chart because the first thing you needed to do is you needed to find the period for each spring and plot that against the spring constant for each spring. So what I did is I made a column first of the measured periods for spring A, B, C, D, E, and G, all the way through G. And then I just recorded the spring constant that the lab gave me for them. I didn't have to make any calculations. And you notice that when you do that, it looks like an inverse. It doesn't look like a line at all. It looks like some kind of inverse function. So I'm going to see if I can't get an inverse here and see if it looks like it. It looks kind of like it, right? But it's not quite like it. It would have to be tweaked a little bit. But it's like some kind of inverse square or something going on there. So, it's some kind of inverse looking, inverse square type curve, but it's not linear. So I could look and maybe I could do a square law and see if that works. That doesn't work. I'm kind of limited as to what I can put in here, but it's some kind of inversey looking curve. Okay. So I know that the higher the spring constant is, the stiffer the spring is, the smaller the period is. That means that it takes less time for it to bob up and down once. And so that means it bobs up and down really, really fast when it's a stiff spring. And when it's a flimsy spring, it bounces up and down very, very slow. It takes almost, half a second to go up and down versus a tenth of a second. So to straighten that out, according to our formula, t squared is proportional to 1 over k. So what I did is I made a calculated column. I went to change formula, and I just said t, and I just chose the period, and I used the caret button, and I squared it. Okay? And it did it for me automatically. And then for the spring constant, I changed this formula, and I took the spring constant, but I did 1 over the spring constant. That's what I typed in, 1/spring constant. Okay, now when I plot this, if I plot period squared versus the inverse of the spring, I get something that looks more linear, but it's not perfect because of the error in making these measurements. Okay, but I can tell you that it is linear because you see this RMSE, it's 0.16 times 10 to the -2. So that's 0.0016. That's 0.0. So if the RMSE is 0.0, that means it's a good fit. So this is, oh, wait a minute, it's got k squared. I wonder why it's like that. Let me just look at my formula and make sure I didn't mess up anything. I might have. Here, let's clear this out. And I did 1 divided by the spring constant. Okay. So this should be some kind of linear fit. Let me do that. Oh, that's why it wasn't coming out right. Okay, so it's a very small RMSE. Okay. And yeah, it doesn't look great, but it should be linear. And then you want to ask yourself, then you did that right. That looks great. Number 3 looks wonderful. Number 1 looks great. Then it should be an inverse function. That's right. And then it should be directly proportional 1 over k. That's right. Now, what would you expect to be true? The period is very, very small. If the period is very, very small, then k has to be huge, has to be approaching infinity, right? Because it's an inverse relationship. And if the intercept of your graph, what's the intercept of your graph? Well, it should be 0 because when you have no spring constant, you should have no period. So when you look at that intercept is in fact very, very small, times 10 to the -2. So it's very, very small. And then look at the slope of your line, and we talked about that in class, that you're going to convert that slope to a number. So later on, but if you look at your slope is in newtons per meter, and so you should be able to use the slope and everything to figure out what the units are of the slope. All right. I don't know if that's helping or not. Maybe I might need to meet with you. So just let me know. But you don't have to do the graph anymore because I did that for you.